Welcome to chapter 3 of making your own development board. In chapter 1 we saw and selected a particular microcontroller called CH552G, which is a 8051 based microcontroller which is 8-bit microcontroller with various peripherals and interfaces to work with. Chapter 2 we saw what are the power requirements of that particular microcontroller. In chapter 3 we will be getting hands-on for schematic setup. We'll be using a software called Kicad. Kicad you can directly download from Kicad or GitHub. So Kicad, if you just Google Kicad or Bing Kicad, you will go to kicad.org, which is the site. You can go to downloads, download the flavor that you want, and this is how it would work. Right, I have already installed Kicad. I'm opening that particular thing right now. So the latest version Kicad 9 is what I've installed. You can go with Kicad 8 or 10 if once that comes out, right? So once we do that, I'll be opening this particular new project. Here we have devboard. Let's delete that. I had created that dummy project. Let's say we want a project called CH552 dev. So we have, once we create that particular project, two things pop up. One is schematic and one is PCB editor. So this page is your schematic editor and this page is your PCB editor. First we need to build our schematic, then take that schematic to PCB editor. Then we can edit our PCB or create our PCB. So just a bit of housekeeping. All the key presses that I do gets posted on my left hand corner. So once we are here, we can click on load symbols, or A is the shortcut, which would start loading symbols. So I'll just describe, by the time that gets loaded, I'll describe what are the menus that we have here. We have component placement menu, power requirement menu or power components. We have buses, then normal blocks, no connectors or tap connectors. These are labels. These are zones. All right. Then this is hierarchical sheet. Again, a global label, hierarchical sheet, text, text box, table, rectangle, circle, arc, things like that. So this is how this works. And we have other menu items here, which are save. Then you have your configuration sheet. This particular icon belongs to setting up this particular drawing sheet. Then printer, plotter, paste, reverse, forward, zoom in, zoom functions, all these things. Then moving things sideways, upward, then mirroring, flipping. Then comes your other set of icons which are on your editors, right? Pin editor, searching of components, labeling of components, ERC check, electrical rule check, whether all things are correctly mapped or not. So we can go over each. This is symbol editor. This is symbol library browser, footprint editor. Then this is annotating schematic, ERC check, electrical rule check, simulator. This also comes with a simulator, but we will not be utilizing that. Assigning footprints, then you edit symbol fields, then generating bill of materials, and switching to PCB data. These are the basic things that we will be utilizing. This belongs to grid, whether you want grid overrides, things like that. inch, millimeter, mil, so we'll be using millimeter as default. Full window crosshair. Now our crosshair is just 2 lines, so this is full window and this is normal. You can even have full window if you want everything to be organized, right? Then show hidden pins if you have hidden pins. Line mode for wires and buses. Draw and drag at any angle, and this would be very strict 90-degree angles, and this would be 90-degree and 45-degree angle. These are annotate automatically. Then hierarchical and property pages, right? Before we get started, one thing which I want to do is Kicad doesn't come with automatically CH552 library. That needs to be added manually. So if you search for CH552, it doesn't have it. So what we can go do is close this, go back here, go to preference, symbol libraries. I want this to be very project specific. So what I will do is CH552, sorry, library path. I have my library somewhere stored here in this particular folder. I'll link this library CH552 Kicad. So once I click OK, again this will take a minute to load that particular file into the library, and it would be available for this particular project. Yep, so that got loaded. Now we can add even the footprint of this that particular library. Let's again call CH552. It would be better if you have the same nickname for both libraries so that it becomes easier for you to remember. We need to capture the pretty extension folder and say OK. So everything under that folder will be browsed by this particular footprint library. Again, it will take a minute, and we'll get back once that gets loaded. Yep, now that's loaded. We can go back to our dev sheet or schematic sheet and search for CH552. Here is CH552. It doesn't have a default footprint, but that's okay. We'll attach a default footprint later, right? So now we have this particular CH552. We need to traverse back to our data sheet to see the pin definition. So 16th is the VCC pin. Again, you can see 15th is the VCC pin. Here they have already defined it as VCC. 16th is 3.3 and 14th is ground. So this is what we are working with. So each of them have to be coupled. The power pins needs to be coupled with 0.1 microfarad. So let's say I require a capacitor of 0.1 microfarad in, let's say, I'll go with 0603. It is a small footprint, but that's okay. So that is done. Let's make it here. 3.3 volts goes 3v3. So we'll take a power symbol here, plus 3v3, attach it with respect to 3.3 volts. Again, take a power symbol for 5 volts, attach it here, and take a power symbol for ground and attach it somewhere here. So I'm drawing a wire between these, right? So it becomes easier for us to identify. So now that is taken care, what we can do is we can take this 3.3 volts and attach it to a capacitor again here, and this needs to be decoupled with respect to ground. So I'll take ground, put it somewhere in between, connect both of them. So this is our decoupling circuit. That is done. Let's keep it someplace safe. Right. So we have done decoupling of power. Once we have 5 volts power, that gets directly decoupled with respect to VCC pin and 3 volts 3 pin. So the primary question now comes, where do we get 5 volts from? So that's where we need to traverse back to our block diagram. Here we had decided that we'll get the power from USB, so we have to design that USB as well. So our current design of USB would be only with respect to power. So we'll be taking USB-C 16 pin, which would be working as USB 2.0. So I'll be selecting this receptacle because this is what is available directly to me near my Radio Shack or local electronic shop. So again, one thing that you guys need to note is all ground planes should be connected. We cannot have multiple ground planes. We don't have any use for these two pins, SBU1 and SBU2, because those are specifically for high speed communication, and we are no longer we will not be doing that, right? So now multiple considerations with respect to power, because we have used USB-C. There can be two kinds of cables. One is normal USB type A to type C cable, which would provide 5 volts at around 2 amps max, or USB-C to USB-C, where power negotiation might happen. We know that our circuit is maximum capable of handling USB 2.2 data structure, or the way USB 2.2 operates. So we need to make sure that my USB also talks to the power delivery or power negotiation chipset on the other end and say that, okay, I am capable only of taking USB 2 or up to 500 milliamps or 1 amp, 2 amp, things like that. So for that, we have to make sure that we configure CC1 and CC2 pins carefully. So we'll take resistor here. Again, I'm keeping all at 0603, and this should have a value of 5.1k. So we'll place it with respect to this. So once that is done, we can connect these two. Take ground for that matter here. Okay, this is with respect to power negotiation of USB 2. If you guys need more information on why I have selected 5.1, please look Google out saying that power delivery mechanisms for USB-C using 5.1k resistors on CC1 and CC2, right? You'll get a lot of articles. There is an article from Kicad, right? That also helps you understand what are the different values that you can put if you want to increase the power delivery, right? So let's say I'm using this particular power delivery and with PD chargers, then I'll not be just connecting this. I'll be utilizing this CC1 and CC2 with respect to, that would be very specific scenarios. With respect to this, you see here CC1 and CC2 pin 2 and 3 with respect to this, in order to power negotiate on the VBus. The VBus data can be captured from here, VBus 1, VBus 2, right? VBus 2, there should be VBus 1 as well. Where is that? Yeah, pin 1. So that can also be done. but here we are keeping things simple. So let's say VCC here, because this might have somewhat, usually if we have this at 5.1, this gives 5 volts, just to make sure that if someone connects directly on the pin here, I want to make sure that we have a safe this thing. Let's use a diode. Again, this would be 0643 diode. So we'll take the 5 volts from here and plop it over here. Yeah. So this is with respect to power delivery for this. So how it works? I connect my USB cable here. I'll have ground. I'll have USB power. There would be CC1 and CC2 if I'm using USB-C to USB-C, which would do the power negotiation with respect to the other side and give us pure 5 volts here. If I'm just keeping this as for the namesake, even if it is not there, it works, right? We'll have a diode in order to have no current passing. This would be a Schottky diode of, let's say, 0.3 or 0.4 volts drop, and we'll get 5 volts. If it is not there, you can just use a 0 ohm resistor in order to short it out as well, or a simple wire connection between those would also help. So what we can do is, in order to minimize on the space, let's plot this somewhere here for power negotiation and use this also, because I said it is optional. Let's make sure that we have something without this T as well. I'm gonna put a solder jumper, which is bridged. So I'll place that here and connect this. So only if we require, we'll put a diode here and cut the solder jumper, otherwise not necessary for that. So VCC and 5 volts would be same if we do not plot in the diode. So that's what we had talked on schematic, right? That would be the start of your schematic. How do we place components? How do we change the values? So here we learned about changing values by pressing V, right? It would open your edit value field. I have to edit a value here as well, 5 volts and this. So this again, there is another way. If you go to properties, you can change the values in bulk. So here we have entered 0.1 microfarad, right? Here let's look for a Schottky diode. I'm looking for 0.3 volt Schottky diodes and rectifiers. Let's not worry about it. Electron. I'm looking at my local window. So this might be the one. Again, we might have to change the symbol for that. It might not be point 0603. So here peak current is 1 amp, blocking voltage is 40. I need to check on what is the dropout voltage for that. Or we can go with 40 volts 1 amps. Again, this and that, it might look very similar. Let's see what is the dropout. Forward voltage is around half a volt or less than half a volt at 25 degrees centigrade, right? So around half a volt is good enough. So we will use this particular Schottky diode, which is DO214 AC, or we will have SS14 package. So let's look for Schottky diode itself, which can replace this. Let's see if this particular, it's not that. So I'm selecting Schottky diode with what is the package of this? SMA case 403D2. So we need to look for that. SMA we have our SMA here. So we'll select that, put it, delete this. So we have put in Schottky diode here. We have everything with respect to power constraints figured out.